The discoveries of the James Webb Space Telescope have subverted the case for the theory of the universe's origin. The James Webb Space Telescope has recently conveyed an exhilarating revelation that is sending shockwaves through the universe of material science. Through a single amazing picture, it has obliterated long-standing discussions, leaving researchers paralyzed. The period of theory is over, as Webb's most recent catch is both outwardly enamoring and a game-changer that vows to reform our impression of the real world. What searing discussion among researchers has this picture conclusively finished? And in what ways is the staggering image caught by the James Webb Space Telescope reclassifying how we might interpret the universe? Join us as we dive into why James Webb's discoveries are stopping discussions in physical science. The basic issue with astronomy is that researchers can't come to an understanding about how old the universe is or how quickly it is extending. This unanswered peculiarity has bewildered researchers across ages, driving them to conduct various investigations to find answers. Cosmology is the field of research that spotlights on getting to know how the universe was made, how it is set up, how it has changed over time, and ultimately how it will end. This field has seen significant advancement in the past 100 years. The currently accepted cosmology model, the theory of the universe's origin, proposes that the universe has been growing from a very hot and thick introductory state for about 13.8 billion years. This development is estimated by the Hubble constant, which shows the speed at which the universe is extending. However, estimations of the Hubble constant are not direct. Estimating the Hubble constant can be broadly classified into two groups: local estimations and early universe estimations. Local estimations include the investigation of galactic bodies, for instance, Cepheid variable stars and type Ia supernovae, which act as standard candles to measure the Hubble constant. Because of their luminosity, space experts can measure how the universe's development influences the paces of these objects to conclude their distances and thus ascertain the Hubble constant. The second group is the estimation of the early universe. Researchers use observations of the cosmic microwave background radiation, CMB, the luminosity of the Big Bang, found during the 1960s. The CMB shows the microwave radiation of the early universe when it was just 380,000 years old. By estimating the minuscule temperature and polarization variations transmitted by the CMB, space experts can lay out the age of the universe and its pace of extension. Yet here's the issue: the aftereffects of these two strategies do not connect. The results observed through local estimations confirm that the universe is growing quicker than what we gauge based on CMB data. Due to these differences, researchers have been striving to uncover the reasons behind the outcomes. As such, further research is being led to learn more about the secrets of the universe. As things stand, the distinction in estimations shows that there is either new science we have hardly any familiarity with or mistakes in one or both ways by which we are estimating things. Because of the James Webb Space Telescope, we can see into the dark universe clearer than any time in recent memory. The telescope can show the slightest and most far-off components, planets, and galaxies we wouldn't have thought it was feasible to see. Due to its capacities, researchers expected that information from the JWST would help us definitively compute the Hubble constant. However, the principal wave of information has astoundingly made matters more muddled. They have given us new insights that are not consistent with what we assumed we knew. Might this information at any point lead to a new hypothesis and reform how we ponder space? Assuming this is the case, we could have to audit how we interpret how the universe works. For example, we may find particles and powers that have never been noticed, or it could imply that dark energy, an unexplored world factor liable for the speeding up development of our universe, should be reevaluated. Up until this point, the manners in which we think about space have advanced as we proceed to discover new things. For instance, in 1965, when specialists found the cosmic microwave background radiation, it filled in as a strong basis for the thought of the theory of the universe's origin. Before then, researchers believed that the universe was everlasting and consequently was continually extending at a uniform rate. Yet, the new proof demonstrated that was not true. Additionally, when we found out toward the end of the 1990s that the universe was persistently extending at a speeding up rate, it further changed our understanding. We found dark energy and its effect on the universe's development. Accordingly, every time we learn something new, we question whether it squeezes into our ongoing structure. If not, we concoct new ways to deal with comprehend the universe better. To this end, the issue we are looking at in cosmology today could prompt the revelation of the most significant answers for the universe. While the issue is challenging, it is also exhilarating, as it constrains us to foster more mechanically progressed devices to investigate space. This cosmological quandary likewise joins the logical community from various nations, as each researcher wants to find out about the universe. Above all, it shows that science is continually changing and developing as we dive deeper into space. Alongside the Hubble strain, there is likewise a concern referred to known as the S8 strain. This is with respect to the spatial circulation of matter in the universe. This can be utilized to draw a primary image of the universe and perceive how it has developed. Cosmologists allude to this peculiarity as unevenness because there are areas of room that have parts of worlds firmly assembled while other regions are inadequate. Researchers will utilize various procedures to quantify this knottiness, and one way is to check how the light from far-off cosmic systems gets bent by the different gravity of enormous items, for example, galaxy clusters. This bending, known as gravitational lensing, gives us a method for exploring where dark matter is, given that it is imperceptible, as it doesn't discharge light. Scientists additionally utilize the cosmic microwave background, CMB, a glimpse from the very outset of the Big Bang. This light has been moving for roughly 13.8 billion years, bearing news from the early universe. Through CMB examination, physicists can disentangle how the universe was knotted in its introduction to the world, which ought to match the observational unevenness of the universe at the present time for a huge scope. Yet here's the catch. These outcomes additionally don't adjust. The CMB's knottiness, presented by the non-round gravity appropriation model, infers that the matter appropriation at the beginning phase of the universe was more homogeneous compared to the one noticed involving gravitational lensing. As such, we can figure that there is something else that we are not considering in the explanation. This takes us back to the idea of dark matter. What precisely is dark matter, and how does it work? The truth is, the issue remains unanswered. However, all hope isn't lost, as the James Webb Space Telescope, JWST, is set to rethink the field of space science with its exceptional high resolution and responsiveness. The telescope will inspect early periods of the universe and examine the main galaxies and stars formed. This makes it conceivable to further improve estimations of vast extension and matter conveyance. These basic questions will require exact perception and potentially new approaches from a hypothetical point of view to figure them out, whether or not the end is seeing as more significance to dark energy, finding totally new physical science, or in any event acquiring a superior comprehension of dark matter's conduct. The ramifications will be expansive. Processing the secrets of the universe is like resolving a zillion-piece puzzle blindfolded. Researchers should be visible as intensive analysts who are centered around and fixated on tackling these secrets. The most recent endeavor, called Project Flamingo, is evidence of NASA's heightening enthusiasm for logical investigation. Utilizing one of the world's most exceptionally acclaimed supercomputers, arranged at Durham College in England, Project Flamingo is a totally breathtaking accomplishment in the realm of computational advancement. It costs more than 50 million hours of PC time and highlights 30,000 processors and counting. The activity features the academic community's resolution to explore the universe completely, significantly zeroing in on dark matter. Dark matter, the secretive substance that neither emanates, absorbs, nor reflects light, is gathered to exist because of its gravitational effect on noticeable matter. This tricky nature continues to intrigue researchers. However, the methodology of Project Flamingo is unique in relation to past reproductions. It includes all potential types of inestimable components, from systems with the most unique gas content to stars and black holes at the center of the universe. Through such an arranged technique, the slow change in the portrayal of the universe was made from a fundamental milestone sketch. The inspiration behind aggressive undertakings like Project Flamingo is clear: to explain vast struggles where the estimations appear to be broken and do not fit into the construction of the universe. This dissimilarity in estimation recommends a fundamental misconception in our ongoing understanding of the universe's operations. If these measurements can be contrasted with melodic types, they are like jazz and classical, each having its own strategy, albeit still related. Flamingo endeavors to join these disparate perspectives and hone our individual impression of the universe. Anyway, in spite of its complexity, the vast pressure perseveres. This strain keeps on existing as lowering proof that we still can't seem to tackle a significant part of the secret that encompasses us. The universe's secrets are mind-boggling and continually changing since the moment Edwin Hubble made his shimmering disclosure of the growing universe in the mid-20th century. The speed of our cognizance has been astoundingly quick. Researchers are reliably making unique discoveries about the elements of the world, like the theory of the universe's origin, dark matter, and dark energy. The James Webb Space Telescope has just started a new age in cosmology that guarantees much more. The observations made by JWST will help bridge the gaps in our comprehension of the universe, potentially altering our perspectives on its structure and evolution. As we continue our quest for understanding, each revelation adds new pieces to the puzzle, leading us closer to grasping the universe's profound mysteries.